So the very first kind of physics scenario we want to understand is how distance and time and velocity, those three variables, are related to each other. We already talked about distance and time being fundamental variables in physics, and we're going to learn about velocity and how it applies. Now, as is often the case, we're going to start with a graph, because a graph lets us see trends that we won't be able to see in individual data, and those trends are going to then help us to build equations. So the first thing to do is to figure out what we can do to make a graph that is meaningful to help connect some of these variables. So let's just say you went outside, someone ran around a bit, which we're going to do at some point in class, and we took some data about that person's distance and at what time they were at specific locations. And you decide to come back in and make a graph of the distance and the time. Well, the first thing to do is to decide where those variables belong, on which axis. Well, the time is always going to be an independent variable, because that's the one thing that you can't control. Time just keeps on marching on, so we're always going to put time on the x-axis of any graph. That means that distance is the dependent variable, which goes on the y-axis. It's the thing that the distance or the location of the object is going to depend on how much time has passed. As you put those on the axes, please don't forget to put your units. So in this case, we measured time in seconds and distance in meters. Then make sure you choose a range that is just barely larger than your data set. In this case, my time data went from 0 to 100, so I picked a range that went to 120, so a little bit bigger. And my distance data went from like 7 up to 40, so I made a range that was 0 up to 45. So the reason you want a range that's a little bit bigger than your data set is so that your data gets stretched out throughout the entire graph. That helps you to see those trends much better. Go ahead and put the data points on there, just like I did. Be as accurate and precise as you can. I actually like to use little X's instead of dots sometimes, because I feel like those are less likely to get lost in the shuffle of the graph, but it's up to you. From here, we're going to draw the best fit lines, and we've talked about those, that match your data. Sometimes you can't tell whether a line or a curve is going to be the best choice to go through there, and in that case, you're going to always want to pick the simplest line that works. In other cases, like in this case, you might need multiple best fit lines if your data has distinct intervals. So in this case, I would say I see 3 distinct intervals. I see one chunk at the beginning where there's kind of a down slope line, and then there's like a flat line there for a little while, and then it slopes up. So I would actually make this into 3 different chunks, 3 different best fit lines for each of those intervals. So my best fit lines would look something like that. So once you have your graph with your best fit lines, it's worth asking ourselves, what do we want to learn from this graph? What features of this graph are interesting or tell something useful? Well, the first thing that I notice immediately is that some of those lines are slanting up and some are down and some are flat. So what do I suppose that that's going to tell me about this graph? Second thing, they have different steepnesses. Some of those lines are very steep and some are more shallow. What is that going to tell me about the motion of the object? The third, those lines have different lengths. What will that tell me about the motion of the object? And the last is always a good idea on graphs to take a look at x and y intercepts to see if you can learn anything else about the motion of the object. So the first trend has to do with the direction of the best fit line. This is a new graph that has 3 objects on it. It has a purple car, a blue car, and a green car, and they have, well, one of them has an upslope line, one of them has a downslope line, and one of them is flat. So the question is, if you look at this graph, and I'd like you to take a second without just listening to the answer, to think about how does the direction of that slope tell us something interesting about the motion of the car. So the slope of that line tells me, generally speaking, whether that car is going forward, backwards, or stopped. The purple car goes from a starting spot of 0 kilometers up to 3 kilometers, so it's moving in a direction that you could choose to call forward. You could also call that north or whatever you know about it. But the key thing is when we get to the blue car, which starts at 4 and goes to -8 kilometers, it's going to be moving in the opposite direction because it has the opposite slope. So whichever way the purple car is moving, the blue car is opposite. Maybe it's forward and backward, maybe it's left and right, maybe it's up and down, or north and south, but they have to be moving in opposite directions. This doesn't mean that the blue car is actually having to drive in reverse. Okay, it can actually be in drive. It's just going to be pointing the opposite direction, moving the opposite direction than the purple car. The green car, of course, starts at a distance of 3 kilometers and stays there the entire time. So when you get a flat line on this graph, that tells me the object is actually stopped. The second thing I'd like you to think a little bit about is how the steepness of the slope of the best fit line, what that tells us about the motion of the car. So how is the purple car and the blue car and the green car, how is their motion different in this graph? They're all moving the same direction this time, which is backwards, or left, or down, or however you want to define it. But the blue car starts at 4 kilometers and ends at about -8 kilometers, while the green car started at -7 and only ended up at like -1/2 in the same amount of time. So if you think about those two vehicles, hopefully it'll occur to you that how steep the slope is of this graph actually determines the relative speed, fast, medium, or slow, of the object that you're interested in. So which car is faster, that blue car or the green car? Hopefully for everybody you're saying the blue car is faster. It covers a lot more distance in the same amount of time as the green car. The next trend I'd like to reference here has to do with the length or duration of the best fit line. This one's probably pretty intuitive for you guys, but the length of the best fit line is going to tell us how large or small the time interval is. So that green car is standing still for 2 minutes, and the purple car is moving forward for 6 minutes, and the blue car is moving backwards fast for 4 minutes. So the amount of the length of that line just tells me for how much time the object is actually engaged in the motion. The last thing I wanted to chat about is the intercepts of the graph. So we've got a purple car and a blue car here, and the purple car intercepts the distance axis, the y-axis, at 0, and the blue car intercepts the y-axis at 4. What that means is, those cars started at different spots. The purple car started at some place that maybe I defined as my origin, and the blue car started at some place that I defined as 4 kilometers away from my origin. You could also look at the x-intercepts. In this case, the blue car intercepts the x-axis at 2 minutes. So that means after driving for 2 minutes, that blue car is finally located at my origin, or wherever my purple car happened to start. The purple car starts at that origin, but it never comes back there. So if the origin is your house, for example, purple car is going away from home, blue car came home and then left again. So that's what the significance of the interception is. Summary of this video: make sure that when you're looking at your graphs of distance and time, you're looking at your best fit lines and not the actual data points, that you've carefully made those best fit lines, because those are the things that really tell you the trends, not the data points themselves. Second, you can learn something significant from the direction, the slope, the size, and the intercept of each line. So be a careful evaluator of your graphs.